So, did I ever orient this? I don't think so. Oh, I don't want to work today. Damn, I gotta sit down. I hate sitting down. Okay, so sorry, internet audience, here we go. Maybe technical difficulties. So we know that polar equations are things like r equals some function of theta. We know that parametric equations are something that x is some function of a parameter, maybe t, and y is also some function of a parameter t. It turns out we can blend polar and parametric together to make graphs that are kind of hard to do or challenging to do either way. And the catch is related to our triangle that links us between the polar world and the rectangular world. So given some angle here, we have our x value here, our y value there, and our radius there. And we know that in this triangle, x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And this allows us to parametrically draw polar graphs. So, for example, thinking about the flowers we drew earlier, the function r equals cosine of 2 theta will be a 4-petaled flower. To draw that parametrically, we just combine it with this stuff right here. And so parametrically, x would be, this is my r, it would be the cosine of 2 theta times the cosine of theta, right? R times cosine, and y would be r times sine, which should be cosine of 2 theta, because that's my r, times the sine of theta. So I'll just demonstrate that in Desmos that I could graph it polar ways or parametric. And it kind of depends, on how you want to do it. So if we wanted to watch something trace the path of a rose, we would have to do it parametrically, because it doesn't work that way polar-wise. And let's see, and I could do it with this crazy curve too. So let's just go simple for a sec. R equals cosine of 2 theta gives us that rose right there. Parametrically in Desmos, we have to use a point. My x value of my point would be that cosine of 2, let's see, I have to use t with parametric. So cosine of 2t times the cosine of t is my x value for my parameterization. And the y value would be r, which is cosine of 2t. And let's turn this guy off for now, times sine of t. And so it should draw that rose out. And so if I extend it beyond 1, like over 2 pi, it'll give me half my rose. If I go out to 2 pi, it'll give me my whole rose. And so I could put a slider on this to make it graph it out for me. So if I turn this one back on, you can see they are one and the same graph. Okay, so we can always parameterize polar, or we could parameterize rectangular. And the idea of a parameter, it allows us to trace it out in time, and we control how the speed over time. Okay, I guess I should demonstrate that since I mentioned it. So let's get rid of view and make a slider called, what are we going to call the slider? I'm running out of letters. How about A? Oh, I didn't make A a slider. How do I make a slider? Maybe I have to do it in here. A. Oh, there we go. Make A a slider. Okay, so the trick with parameters and sliders is you have to multiply the slider in everywhere you have a T. And then you let T only go up to 1, then the slider gets to control the action. Pretty sure I did that right. So right now my slider, oh, I didn't turn it on. There we go. So if I go and let's see, my slider, I probably should go from 0 up to 10's fine. And step just means how often do you want to increment your sliders, like your delta x. Okay, so then I could start at 0 and then I can watch this thing being traced out. If I want to put a point on the end to see the point move, I have to write it up again and as another element. And then I could also put it at 0 and say, okay, play this for me. Once it starts retracing itself, I can't see it anymore because I can't see the endpoint. But if I wanted to change the speed it's being traced out, let's change the slider A to only go up to, let's see, we have, what's the period here? 2 pi, right? Change the speed, I would just have to multiply something by t. To make it go twice as fast, I would multiply t by 2 everywhere. We should see it getting traced out quite a bit quicker than if the 2 wasn't there. And it also changes the period. So remember we talked about the difference between speed and slope the other day when you have a parameterization. So it doesn't matter that I doubled all the t's in here, it's exactly the same graph. And if I pick a particular point like this one, it's gonna have the same slope whether that 2 is in here or not. But the speed at which we fly through that point is going to change based on this multiple I put in right here. Okay, so we'll look at speed again in a moment. Okay, so parameterizations versus polar stuff. We need to get back to the problem we started yesterday, which is an ellipse we were going to play with, and the semi-major, the major axis. Well, I guess A is called the length of the semi-major axis. And I think in class I said we were going to let A be 5. B is usually what we call the semi-minor axis. And I think I wanted that to be 3 the other day. So if I graph this, I'm going to do the, let's see, we're doing parametric. So I think the equation, if I center at 0, would be x squared over 5 squared plus y squared over 9 squared equals 1 in rectangular. The parameterization I came up with the other day, x ends up being 5 times the cosine of, let's use t, and y ends up being 3 times the sine of t. So either this rectangular equation or this parametric equation are going to give us exactly the same graph. To get the full ellipse here, I would want t to range from 0 to 2 pi to get 1 revolution through there. So 1, 2, 3, 4, 5. There's 1 endpoint. 1, 2, 3, 4, 5. There's another endpoint. Up 1, 2, 3. Up 1, 2, 3. And just a note why I'm using the terms major, minor, and semi. The horizontal axis is from -5 to 5. So the horizontal axis actually has a length of 10, right? The value of A is half of that full length, hence we call it semi. Major because it's the bigger of the two. Minor because it is the smaller of the two axes. And then my curve, my ellipse, sits in between here. So something like this. When we graph something in parametric, we always want to plot some points so we know the orientation of the graph. So just to double check that here, plot a few values of t, x, and y. If t is 0, cosine is equal to 1. 1 times 5 is 5, sine is 0, so I'm at this point right here when t is 0. 5, 0. And if, say, I let t equal pi over 4, at pi over 4, we get square root of 2 over 2 times 5. So calculators, please. Anybody get one? So the square root of 2 over 2 times 5 is about 3.53. So let's call it 3.5. The sine is the same value. So if I multiply 3 by 3, I get 2.1. So I should have the points 3.5, 1, 2, 3.5, and then 2.1, which is kind of on track where I have that. That would be about right there when t equals pi over 4. So it's about 3.5, about 2.1. At pi over 2, I'm going to get the cosine is 0 and the sine is 1, so I'll be over here when t equals pi over 2. And so we can see that the orientation of the curve is like this. And usually only takes a few points to figure it out. If it's a more complicated curve like that crazy rose, then you have to plot more points, because remember with the rose, I think that I parameterized that sucker over here somewhere. Yeah, with the rose, it traces out petals starting in the first quadrant, then it jumps to the third quadrant, fourth quadrant, then it's going to jump into the second quadrant, back to the third quadrant, over to the first quadrant, back to the second quadrant, right? So it's a lot more complicated in the path that it makes out. But we usually try to draw arrows in. And also when we do a parametric plot on paper, we want to indicate a couple of values of t to figure out where the heck we are. Like over here, I'm pretty confident that's going to be when t is pi. And this point down here, I'm pretty confident now is going to be t is 3 pi over 2. And then finally, I get back to that same point when t is equal to 2 pi. Okay. And so we can use a calculator and graphing calculator to help us figure out the orientation of the curve. Now, taking a look at this right here, my y value is increasing, true? All right, so dy dt is positive in this region right here. On the other hand, I'm heading left, right? My x values are decreasing, starting at 5, going down to 0. So what's dx dt in this region? It is negative. And that's a problem when I go to calculate area with the parametric formula. So that's my next goal here. I want to find the area. And area for parametric is always the absolute value of the integral as t goes from some starting number to some ending number of the y function times the x function's derivative with respect to t. The absolute value means I have to check when do either of these change sign, because that's going to totally mess me up. So we have to know both. When is y positive and when is x prime positive? Because if either of them change sign, that means I have to break the integral into pieces to be able to deal with the absolute value. Because remember, absolute value is a piecewise function. Right? It says do one thing if it's not negative, do something else if it's negative. So let's finish our evaluation here. New page. We know that y is equal to 3 times the sine of t. And that right there, we are positive if t is between 0 and, let's see, sine function 0 and pi, right? The sine is positive. And then we have x prime to deal with. Now, just a note, usually a prime means with respect to x. When someone takes the derivative with respect to t, in a lot of books, you'll see a dot over the top. So a dot on top means you took the derivative of that variable with respect to time. And I'll use that notation occasionally. And so my x dot, so the derivative of the cosine is the negative sine. So I'm going to have negative 5 times the sine of t. And note the negative sign, that's going to be down here between 0 and pi, right? So for my area of my ellipse, I think what I would like to do is, I know an ellipse is symmetric, so this region, this region, and this region, and this region, all four of those have the same area. So I think I'm going to go for 4 times the integral from 0 to pi over 2. Oops, wrong button. So switch colors. So I want the absolute value of the integral as t goes from 0 to pi over 2. I'm going to take 4 times that. And then the integral formula says take your y function, that's 3 sine of t, multiply it by dx dt, that's negative 5 sine of t dt. So that's technically the integral we need to get the total area here. If we just integrate blindly, we could cancel stuff out, right? So we want to be careful about that. So if we just tried to integrate this without absolute value from 0 to 2 pi, we get nothing. Stuff's going to cancel. So we always have to think about it. Now, what does the absolute value do here? Well, the absolute value is just going to crush that negative sign, right? Cool, I can deal with that. The 3 and the 5, they're going to pop out. So I can rewrite this then as, let's see, 5 times 4 is 20 times 3 is 60. Am I doing that right? Oh, shit. Shoot. Ooh, sorry. Jinkies. It's pi over 2. Yeah, I don't know why I wrote. Yeah, I think this 4 over here must have got stuck in my head. I don't know. All right, so we have a 60. Did I get the 60 right? I think so. Times the integral from 0 to pi over 2. And usually at first, I write the variable I'm integrating with respect to down here just to remind myself, I'm not using x, I'm not using y, I'm using t. Once I've established that, I usually don't bother writing it again. And then we get sine squared, right? All right, let's see, sine squared, that comes up in the half angle formula for trig. And my recollection is, let's say I got a blank slate back here, that the sine squared of, let's put an x in there, is 1 minus the cosine of 2x over 2. Clint is nodding that I'm getting this right. Feel good about that? Okay, Clint. Cosine is the plus, yeah, and right. Yeah, yeah. And all of these formulas with the squares are the result of the cosine double angle formula. So cosine is always in here, never sine over on that side. Okay, so I'm pretty sure that's right too. So that means this is going to be equal to 60 times the integral from 0 to pi over 2. And then now I have 1 minus the cosine of 2t over 2 dt. So let's see, I think we could take this 2 into the 60 and get a 30 out of that. And then we just have to integrate 1 minus cosine of 2t, which isn't too bad. So new page, let's see, antiderivative for 1. So we're still getting area here. And we have a 30 hanging out front. Let's see, antiderivative for 1 would just be t, right? Then we have a minus. Antiderivative for cosine is sine of 2t. Now, when we take the derivative of sine of 2t, there's going to be there should be a multiple of 2 sitting out front, which isn't there. So I have to compensate with a 1/2. When in doubt on a problem like this, do a u substitution. So over here, you could say let u equal 2t. Du would then have to be 2 dt just for this chunk right here. And we're missing that too, which means we need a 1/2. All right, I feel good about that. Evaluating our boundaries. We get 30 times parentheses pi over 2. Now let's see, the sine 2 times pi over 2 is pi. The sine of pi is 0. So I'm going to get a minus 0. And then minus, plugging in 0, I get a whole bunch of zeros. It's always good to double check those. Just thinking it, sometimes we can mislead ourselves. Yeah, it's not bad. So now I have pi over 2 times 30, which I think is 15 pi for the area. 15. Let's see, is there anything special about 15 and the numbers that we started with? It's the product of 3 and, oops, where's 5? 5, oops. The major and semi-major axis. So we might ask, ooh, is that always going to be the case? Is the area of an ellipse always the product of the semi-major and semi-minor axes times pi, area of ellipse? So let's see if we can reason through that. So is it A times B times pi? Well, let's see. We started off, let's see, we have our 5 and our 3 here, and they were represented, highlighter please, here and here, and they got factored out as part of the 60. All the even stuff canceled out along the way, so yeah, the 3 and the 5 are definitely, that's the only source from them, the A and the B. So if we change that to an A and a B, we would just see the A and B just hung out front the whole time, waiting. So I am confident that, yeah, that is the area of an ellipse. Cool. All right, let's do another ellipse problem while we're on the subject. Let's find the slope of a point on our ellipse here. Let's see, which point shall we go for? Where'd my ellipse go? Oh, there it is. Okay. What do you think? Pi over 4 or pi over 6? Pi over 12? Okay, Clint, man, you're a brave man. Okay, so Clint says we're going to find the slope at pi over 12 right there. So remember I said earlier, Desmos does an awesome job of plotting. Oh, this isn't polar, this is parametric. Okay, never mind. I'm in a different world. We're good. We can plot this point totally. Where's Desmos? There you are. Okay, so let's, do we need you anymore? We're just going to turn you off, close that, make a new one. Okay, so we are graphing parametric, right? So parametric is a point, and we want 5 cosine of t, comma 3 sine of t. And also, I don't know about you, I do love the Pythagorean theorem, but I think the polar version of an ellipse is way, sorry, the parametric version of ellipse is just way cuter than the rectangular version. I don't know about you. All right, check it out. Rectangular, parametric. The rectangular is kind of like, it's nice, but it's slightly painful. Ooh, where'd that square come from? 3 squared is 9, it should not be there. Strange artifact. Anyway, just a little aesthetic thing. Okay, so, and then graphing that, we need all of our 2 pi to get the whole thing. Zooming out. Let's see, to get a point here, all I have to do is plug pi over 12 in there, so I kind of got to retype it. So 5 cosine of pi over 12, there we go, comma 3 sine of pi over 12. And there's my point. Okay, so we're going to try and find the slope at that point. So let's go to the end of the notes here. Come on, there you go. We know again that x first is 5 cosine of t, and y is 3 sine of t. Slope is dy dx parametrically, that means dy dt over dx dt. Shorthand notation of that is a y with a dot on the top over x with a dot on the top. Often you see derivative with respect to time as a dot. All right, so then let's see, what is y's derivative? Derivative of sine is cosine, so it is just 3 cosine of t. And derivative of the cosine is the sine, so that's -5 sine of t. So then we have to evaluate that slope function at t equals pi over 12. Oh, pi over 12, that's a tough one for an exact answer. 3 cosine, oh, it's not that bad. We got the half angle formula of pi over 12 divided by -5 sine of pi over 12. And keep in mind that pi over 12 is 1/2 of pi over 6, right? So we could use the half angle formula on that. Half angle formula, let's see, I think I need a new page and we'll come back. So that's if I'm going for an exact answer, which there's one problem on your homework that does ask for an exact answer. See, can I get this right? The sine of x over 2 is equal to plus or minus the square root of 1 minus the cosine of x over 2. And the cosine of x over 2, so this is just a tweak of the formula we were just doing. Square root of 1 plus the cosine of x all over 2. So our x here is pi over 6, right? Because pi over 6 over 2 is pi over 12. And so that's what we need to calculate our number. Now, the other thing, the plus or minus is there because you got to figure out, well, what quadrant is my angle in? And my angle is in the first quadrant, so I get the plus for both of these. Okay, so we got to think about that. So to calculate this right here, I got a -3/5 hanging out front. And then otherwise I have to use that formula. So let's see, cosine of pi over 6 is what? Square root of 3 over 2? So I'm going to get the square root of 1 minus the cosine of pi over 6, which is the square root of 3 over 2, all over 2. And then in the denominator, no, sorry, cosine gets the plus, that's in the numerator. Sine gets the minus, as Clint mentioned earlier. And so that's going to be 1 minus cosine of pi over 6, which is still square root of 3 over 2, all over 2. Is this going to clean up much? Sheesh. Well, the dividing by the 2 inside the square root, top and bottom, that's going to cancel out. You all with me on that? So that's going to be gone. So then we're going to have a -3/5 times, let's see. Ooh, wait a minute. Oh yeah, no, that works out. 1 plus the square root of 3 over 2 in the top, and 1 minus the square root of 3 over 2 in the bottom, all inside the square root. We could multiply top and bottom by the conjugate, but we just get a messy top and a clean bottom. That sounded strange. I think I'm happy with that answer right there. So then we whip it into a calculator to approximate it and see if it seems like a reasonable slope. So calculators, please. I'm going to type it both ways. I'm going to type it this way and that way just to make sure I did my reducing right. So let's whip out my Google calculator. So let's see, the 3 was in the top, right? So it's 3 cosine of pi over 12 divided by 5 sine of pi over 12. And Google says it's about 2.2-ish. That version. The other version, I have 3/5 times the SQRT of parentheses for the numerator, 1 plus the square root of 3 over 2 in the top, divided by parentheses 1 minus the SQRT of 3 over 2 in the bottom, close the square root. Looks like the same number to me. Yep, same number. Okay, so we have a reasonable answer. So hopefully when you do your online problem, it gives you something nice like pi over 6 or pi over 4. If it's pi over 12 and it asks for an exact answer, I haven't tried. Which problem is that? That's number 3 in the homework. Yeah, mine says use pi over 6. Did yours say use pi over 12 online? Or you haven't gotten there yet? Okay, let's check. I'm kind of curious. So this is 9/4, right? There's a problem just like this. I think it's problem 3 in the homework. Use pi over 3. Okay, so I'm pretty sure it's going to give you a nice number. It's not going to be as complicated as this one. All right, let's do another problem. Let's do the cycloid arc length. So I mentioned arc length the other day. As a consequence of looking up speed. And it turns out arc length here is relatively straightforward. It's the integral as your parameter goes from some number to some other number of the square root of dy dt squared plus dx dt squared, which is just yet another variation of the Pythagorean theorem in calculus. And let's see, we're going to do a cycloid. Let's do the base, should we do the basic cycloid? Yeah, sure, why not? So we're gonna do the cycloid, the basic version, x equals t minus sine of t, y equals 1 minus cosine of t. And if the wheel has if the circle has a bigger radius, you just multiply everything by that radius. Real straightforward. Unless you want to do one of those like prolate or curate cycloids, like the bicycle reflector we did the other day. All right, so in order to do this, we need the derivative of y and the derivative of x, so let's get those. So x dot would be 1 minus the cosine of t, and y dot is just the negative sine of t. I like to do these in stages instead of writing this all out in one shot. So I think I would square these guys next before I plug it in. Derivative cosine is, oh yeah, it was positive sine, correct. Thank you for that correction. Yep, positive sine. So then we want to square those guys. So this thing squared means multiplied by itself. Got no choice. So multiplying that out, I'm going to get a 1. I'm going to get minus 2 cosines of t. And then I'm going to get negative times a negative as a plus cosine squared of t. This one is just sine squared of t. So I'm getting closer. I need to add those guys up and then take the square root. Well, I think I'm at a pretty good place to add them, don't you? So there I added them. But we have this lovely result that cosine squared plus sine squared of the same angle is always 1, plus that one is a 2. So putting that together, I now have 2 minus 2 cosine of t. Okay, so I think we're ready to think about the square root. So new page. So I'm not going to worry about the integral quite yet because I got to clean this up. I can factor out a 2, right? So it's 2 times 1 minus cosine of t, is that right? Yeah. Okay. Well, that's a problem. Oh, but wait. Clint, you're genius. I know that the sine squared of x is equal to 1 minus the cosine of 2x all over 2. Okay, so I don't have an over 2 there, so I could move that 2 over here. So twice the sine squared of x is equal to 1 minus the cosine, cosine of 2x. So all I have to do is say, hey, let's let t be 2x. So if I say t is 2x, then x must be t over 2. So then 1 minus the cosine of t must be equal to twice the sine squared of t over 2. Oh, that's beautiful. Trig identities are amazing, the way they just morph and twist. Okay, like I don't know what they're like. All right, cool. So now we have, let's switch colors, the square root of 2 times 2 times the sine squared of t over 2. Well, square root of 2 times 2 is 2. And the square root of the sine squared is the absolute value of the sine of t over 2. Okay, so now we have to contemplate t over 2 for a minute. Let's see, did we establish bounds of integration for our cycloid? Let's see, the cycloid is this shape kind of like that, and it goes from 0 to 2 pi for t. It is symmetric due to the way it's made, so we could just go up to t equals pi, and we would just have to double that integral. Okay, so now we have to consider, what is our function doing? What's the period of the sine of t over 2? I think it's 4 pi, isn't it? Oops. Sine of x over 2. Yep, it is. So so it's positive the whole length, so we're good. We don't need the absolute value anymore, so that's nice. All right, so I think I would like to do our arc length. Ooh, we got to finish this up quick. By doubling the integral as t goes from 0 to pi, we'll do half of the cycloid and double it. And then this is our remaining stuff. We have 2 times the sine of t over 2. And we just conferred with the sine of t over 2 that its domain is okay. It's always, the sign is going to be positive there. All right, let's do this. We got that 2 out here. 2 times 2 is 4. An antiderivative for the sine is the cosine of t over 2. Now, let's see, if we take the derivative of the, oh, it's the negative cosine. If we take the derivative of the cosine of t over 2, the chain rule says there's got to be a 1/2 out here, but there's not a 1/2. So we have to compensate by multiplying by another 2. And then go from 0 to pi. Okay. Let's see, what do I need to do here? Need more room. So let's just shrink this stuff. Excellent, now we have more room. Maybe we should do that on your paper. Someday we will have paper like this with ink that's in the page and the pen pulls it out and you can move it around. Digital paper, they're working on it. I've seen some variations. Okay, so we have -8 times cosine of pi over 2 is what? 0 minus the cosine of 0, which is 1. -1 times -8 is 8. So I get an 8 there. Just a minor note on this. If we had picked a different radius here, then that radius just gets multiplied through the x and the y equation. We would have then squared that radius here. So there'd be a radius squared hanging out inside the square root. Square root of the radius squared would be the radius. So it turns out in general, for a bigger cycloid, it would just be 8r, 8 times the radius of the circle that made it, which is kind of neat. It just scales up just like a circle does. Well, that was fun and exciting, man. Okay, so we have covered problems like most of the homework problems that you'll encounter in 9.4. So if you haven't started that, please start it. Tomorrow we'll debrief on homework questions on the parametric stuff. If there's still outstanding questions on the polar stuff, let me know. We need to clean that up. And then if time permits, tomorrow we'll talk a little about the idea of a Bezier curve, which is a parametric equation that's used in graphic arts, which is kind of cool. Otherwise, we have to cover conic sections, and then we'll have an exam probably at the end of next week. I will hoping to post a sample exam today, and I will put that somewhere in our course in my open math. All right.